Okay, it is time to start. So thank you very much for coming, and a special thank you for doing a really hard work last night for preparing very good presentations that we are going to hear right now. So what we do have today, it is a summary session that concludes first 3 weeks of our activity. And although in class we were doing some theoretical concept, the major take-home skills is what we train at our evening labs on Tuesdays. And today, I hope you will share your experience about practical skills, so what you can do for your own research project. So here is the list of topics that we will be doing one after one. So it is introductory steps that everyone needs, the practical side of the life of computational chemist. So we are not touching very difficult things. We are doing very basic but important, unavoidable practical skills. How to operate supercomputer, how to prepare a model of your chemical, and how to get any characteristics, how to get something out of the software and out of the computer cluster. So I would like to thank Doug Genuine, administrator of computer cluster. He will try to join our next meeting like this, and I'll also like to thank the Department of Mathematical Sciences who give us this room in the basement of Arts and Science that we use. It is fully equipped for our trainings. And before we are going to start our activity, let me make a little remarks on how we are going to organize our presentation. So it is a really challenging thing to squeeze in 7 presenters in 1 hour, and let's try to make an effort of being short. I know that it is not easy. So the idea is that each talk takes 5 minutes, and since it is takes time to come up front, return back, maybe 1 minute to set up, and also there will be a possibility to ask questions, because it is a strong educational component. Maybe one of you have learned one subject, but the rest of the class wants to ask the speaker how to do it practically. Well, if the questions or talk will take too long, I will start making signs showing like 5 minutes are over, or like waving hands that it is enough. And if the speaker will be too excited and keep speaking, I will just stand up and come here and just maybe tap on shoulder, showing that okay, enough. So please try to be brief. So how do we do it? Those are really baby steps. So definitely the speaker is coming up front. Then the most challenging thing is to mount the microphone. So here is this device. We all are getting broadcasted through the state of South Dakota and videotape. So it is something, you are becoming movie stars. So the microphone is this little box that has some anchor to put on your clothes or put in the pocket. There is a tap for making it on and off. And there is a wire construction that you wrap gently around your ear, and there is a little segment with actual microphone that you want to direct to your mouth. Then you can ask South Dakota SDSU if they hear you or not. It is a best way to check the quality. Wrap it in the form of your ear, put it here, and keep it. It was most challenging part of your presentation. Then you need to find your presentation on this computer, and you can do it the following way. You can either go to the desktop and navigate. Here are 7 presentations, one after another, and you can just click on it and it will go on. So first, second, third, fourth, fifth, sixth, seventh. Or alternatively, you can tap the keys Alt and Tab several times, and then you can switch between windows, and you can look which of those look similar to your presentation. Presentation number 1 is here. Here are my introductory remarks, and then you take the mouse and navigate to this little symbol. Let me show it. It looks like a screen with some inverted T letter to make a slideshow. And then you start presenting with arrows to advance forward. When you are done, you just hit Escape key, like I'm doing right now. And then if you ask something, just reply by clicking. And then before you leave, please take off the microphone and leave it here for the next speaker, because it happens all the time. Taking microphone and going to the back row. Okay, with these remarks, I would like to announce first speaker, Yuchi, Zhang. Will make a presentation about what is Linux, how to operate supercomputer, and what are basic commands.
SD, can you hear me?
Yeah.
Today I will introduce the Linux environment for computational.
Excuse me.
Yeah?
I'm not listening. I can't hear you right now.
Maybe I can just right? Okay. Can you hear me now?
Yeah.
Okay. Computational chemistry is we use the principle of computer science to solve chemical problems. So our objective is we want to get the observable starting from the atomistic model. What is the observable? For example, the structure, interatomic distance, spectrum, and like this. And this flowchart will tell us how computational chemistry works. First, we got the atomic models. Then, based on the Schrödinger equation and other theories, to use the software and hardware to compute the electronic structure. Then we can get the result observables. Then we can present and compare to the real experiment. And doing computational chemistry, we need a cluster. Cluster is a set of connected computers. They work together. So it's like this. So it's more cost effective than a single computer of comparable speed, and so we use the cluster. And for our cluster name is hpc.usd.edu. And all the cluster based on Linux system. Linux is a computer operating system. So why we choose Linux for our system? Because it is a modern, stable, multi-user, multitasking environment on the computer. And the more important is very stable, because the cluster need to work 24 hours. So So a stable system is very important to us. And Linux is free, so we can save money. And how can we log in to cluster? It's very easy to log in cluster anywhere. So we can use Linux system or some software in Windows, such as Party Sigwin. And all the software we need open terminal and type command by using programming language to connect. For example, so this command is to connect to our cluster. Healing Lab is our username and HPC is our cluster name. And the system will require a password. When you type in a correct password, it will get this. So that means you already connected. So HPC, that means you connected to the cluster. And so I will introduce some common commands. First, if you want to enter in a folder, you just type the CD and the folder name. And if you want to create a new folder, so you can type mkdir. If you want to know what's in this folder, we can type ls to list all the files in this folder. If you get lost, you want to know where are you, you can type pwd. Then you will find the directory. Then if you want to fill a file, you can type more, the file name, you can see the detail of this file. If you want to edit, so you can type vi, then you can edit the file. So for example, look here, I already connect to the cluster. I type ls. It will show all the folder name here. We can see we have this folder, our class folder. I want to enter in this folder. So I just need to type sd, the folder name. Then we can look here. That means we already enter in this folder. So then I enter in Dimitri folder. Now I want to look at one file. I just type more. It will show the information about this file. So we do not want to just work on the cluster. We want to download and upload file. There have two ways. One is we can use the program language by using terminal. And first we need in local computer. Then type the scp, this command, and upload, we just use this command. Another convenient way, we can use the software in Windows. For example, these two software. It's easy to just type this and use your username and password. You can download and upload the file. Thank you. Any question?
Okay, let's thank the speaker. Thank you very much, Yuchi. And anyone is welcome to ask questions. Okay, if there are no questions, let's thank Yuchi once again. Very nice presentation. And next speaker is Qiang Wei with explanation of how the graphical user interface can be started and how it can help to build atomic models.
Hello everybody. So today I'm gonna show some slides about Gausview. So in order to launch the Gausview, you have to download a software. It's called Qiang Wei, and well, it's a Linux-like environment, and you input the command in it. So just like what Yuchi shows, and here's a link to shows you how exactly to set up this. If you're interested, I can send you. So I'm not gonna show the things in here. And this was a picture of the X terminal. So for example, like the place we were using for help session, Dr. Keating was the manager, and then we are using the different that desktop as X server, and all our uh, data should go through the where Dr. Keating control. So here's a few commands we use to launch Gausview. So when open the Qiang terminal software, you input the Xwin multi-windows, and at this side of the toolbar, you choose the X term for the sign, and then type the username, which is KillingLab, usd.edu, and the password. Here is CD plus the folder name. We can go into the each one's individual folder, and then go type gv to run Gausview. When the software open, you can see a thing like this, and there will be another window on this side to draw the figure. This button, you press this button, you can see the elemental fragment like this, which you can choose different element and the different type of element in here. Like this was sp3 carbon or sp2 or whichever you need to use. So here I'm still using the benzene as an example. So you choose the sp2 and then it show up like this. You click on the right side here and then click another one to connect them together. Sometimes it shows like exactly what you need, but sometimes it's not. Like what is showed in here is not the benzene ring we need, so we have to adjust it. Here is the since it's like 4 atoms in total, so here is a little function button we can use. It's like 3 atom. We adjust the angles, or 2 atom for the bond length. Here, this one was the 4 atoms. Since we have 4 atoms in here, so we press this one, and then label it 1, 2, 3, 4. It will show up another window in here. So Dr. Keating used to tell us to adjust this one into a linear, but I think sometimes you just change the angle here to 0 will be okay. You don't actually need to put this side into a linear, and then it will go to a part like thing like this, and then you click to connect them together. Sometimes, like this time, it worked directly working. Sometimes, if you don't need to work, you probably need to adjust. Like, sure. Thank you. Is there any problem?
Okay, thank you very much. Let's thank the Qiang. So, any questions from the audience?
Yeah, I had one problem while working with this Gausview. When I make some structure molecules, it sometimes shows bond and sometimes it does not show bond. It just shows the atoms. Can we adjust that to show bonds always?
Yeah, I think it's actually not really important. You right-click on this window, and then they will have like different options. to show different type of bounds. You can choose the hide bound or just show it. They have like function buttons.
Okay.
You right click on this window.
Mhm.
Okay,
You have
and
the option.
two next talks will probably address this question in part. So please listen to the next two talks, and maybe this question will be resolved.
Okay.
Okay, let's thank Qiang once again. And we are very good in following the schedule. The next speaker is Shelton, who will provide more details on building atomic models in Gausview.
Atomic model in Gausview. This presentation, there are 4 parts. First one is what is atomic model. Second one, how to build the model in the Gauss view. Then how to save the model which you have created in the Gauss view. Then how to reload that saved file in Gauss view. What's atomic model? It's an input to the system built by ordering right things from the software. Or in other terms, we can say it's a complete type, like it's called the atomic model. If it is axiomatized by single formula, simply the model of interest, set of ions and the electrons localized nearby. Now, you see, as previously mentioned, once you get insert the GV and get into that, the Gauss view will appear on your window like this. You see, first just click and drag on this window and adjust these two windows besides to each and every, just comfortable to draw your thing, the which model you are going to draw. Here there are some agents, useful agents to build the model in this model making window. I am going to explain just slightly about these each and every agents. Here there is one agent, that's modify bond. Another one, that's modify angle. Just beside to that, there's a modify dihedral, and there's another agent, delete atom. There's another one is here, clean, and another one is here, element fragment. So just if you click on this element fragment, there's another window appear, that is element fragment window. This is just like the periodic table. In the bottom of this table, there are some useful agents to draw the organic compounds. Most of the times it's useful to organic compounds. In this case, just I am going to demonstrate also how to build a benzene ring in this Gauss view and how to save it and how to reload it, the same built model in the Gauss view. Now, just to click on this carbon trivalent, the Gauss view looks and appears like this. Now, move to the other model build window. Click on this window. Now you see the one of the carbon and hydrogen fragments appear on this. Okay. Then next another time you have to click in the end of this bond. Just you see the another fragment will appear and the bond will be made by these two carbon atoms. But now this appearance, it's not comfortable to draw the further benzene ring. In order to make this as a comfortable and the feasible one, I have to go to the Gauss view and use this modify dihedral window icon. Just to click on that and click on this first icon, first hydrogen atom, and then move to click on this carbon atom. Again move to the next carbon atom and click on the hydrogen atom. Once you click on the hydrogen atom, there's another dialog box will appear. In this dialog box, you can adjust or rotate each and every these atoms as you like. Here in this first atom drop down box, when you click it and select as it is a fixed one, the first atoms going to be fixed, and I am going to set this atom 4 has to be rotated. Once you click on this drop down box and then make it as a rotate one, then by adjusting this you can adjust these angles and make these atoms as more comfortable one to build the benzene. Now you see. Now once you have to go to the Gausview and just click on the carbon trivalent icon and again bring that arrow and click on this end of this bond. Now it is okay. Now you see, again click on this. Okay, again. Now once you click on this, now it will okay. But you see, there is a one of the unwanted or additional bond in between these two carbon atoms. Now, if I want to remove this one, what you have to do is, again I have to go to that Gausview, and here there is a one icon. I already explained it. So just click on this and bring the icons here and arrow and click on this bond. Now you see it is removed. Okay, in this next step, these angles and atoms between these in this model is not in a proper manner. So just make it as a in a proper manner, similarly to looks like in the benzene ring. Again, I have to go to the Gausview, and there is another icon called a clean, the shape of broomstick. Just click on it and make it as it will be a more comfortable one, and it looks like really like the benzene ring. Now I am going to serve this model which I created on this one. Now I have to move to again the Gausview file, click on file menu, on the file menu click on save, and here you have to select and navigate where you are going to save, and then write then your name in which you are going to save the model, and click on this drop down button and select the file name as a gaussianinput.com and save it. Click on the save. Now the file is saved. Now if I am going to open that saved file or reload the served file against the Gausview, go to the file menu and click on the file menu and go to open. Again you have to navigate where you have already saved. I saved it already in Shelton. Okay, click on that folder. Now you see that already I saved file. Just click on, select, open. Now the saved model is open in this window. Thank you.
Okay, thank you very much. Thank you, Sheldon. Are there any questions in USD or SDSU? Okay, it was really in good time and very valuable. The next speaker is Mohammad Bani-Khaled, and we are continuing learning the process of building atomic models, and Mohammad will tell even more details of how to fine-tune, how to make additional changes and adjustments to an atomic model with Gausview software.
SDSU, are you hearing me?
Yeah, we can hear.
Awesome. Okay. Well, actually, my previous colleagues here mentioned some of comments I gonna use in my talk. It's very my talk is actually talk about how we can modify distance between bonds and angles plus dihedral angles. So probably if we just, all of you, I think gonna run Gaussian view. Once you run Gaussian view, this toolbar is gonna show up. Once this toolbar show up and draw the molecule, you want to modify distance between two atoms or two groups. So just press this one, this icon. This window is gonna show up, which is show what kind of bond you have and you need, plus the atom 1 and atom 2, which we want to modify distance between both. So once you draw the molecule like this one, for example, and you're gonna modify the distance between any two atoms or two groups, or atom and group. So translate atom, move only the atom, keep the group position fixed in space. Translate space, move the attached group along with the atoms. Fixed, do not allow the atom or group to move. All movement occurs at the other atom. Like for this example, we have in slide 2, we have one fixed, this one, and two translate atoms. See, we move just number 2, while number 1 is fixed. Another slide or another windows show one fixed, two translate group, a whole group, this one, gonna move. So one is fixed, but the whole thing's gonna move. 1, 2 translate the group, so the 1, 2, both of them, see, I am moving the groups, this group and this group. Another comments, once you draw also or working in Gaussian view, we want to modify distance between, as you know, distance is have between 3 atoms. So once you draw the molecule, this icon is gonna help you. So this window show up. You have atom 1 and atom 2, atom 3. All of them has some of commands like fixed, rotate a group. This window show how you can modify the angle. You can, once you click any angle you want to modify. Let's say I want to modify this angle. Just press 1, 2, 3 on the arrows by using mouse. If I want 1, 2 fixed, 3 rotate a group, 1, 2 are just fixed, and you're gonna move rotate a group. Another one you can use also 1, 2 fixed, 3 rotate atoms. This one rotate a group, a whole group gonna move. Another you can do also 1, 2 fixed, 3 translate a group. We're gonna also do 1, 2, 3, all of them translate. If you want also to modify dihedral angle, so you know dihedral angles, if you have 4 atoms like this one, 1, 2, 3, 4, and the dihedral angle actually between you can modify 1 and 4. So you are concerned about atom 1 and atom 4. Both of them has some commands. So this toolbar show you just move this either left side or right hand side to modify the angle between these two atom 1 and atom 4. So you can minus 180 the maximum one, and 180 minus 180 the minimum one, and plus 180 the maximum one, as shows in this window. For example, the distance right now, or the angle between 1, 2, 3, 4 is 180. All of them in the same plane. I would say that's it. You can look Gaussian.com. All the comments are exist over there. Thank you.
Yeah, thank you, Mohammad, for nice presentation and for excellent timing. Are there any questions to the speaker? As this you, do you have a understanding for your previous question, how to set up type of the bond and distance between atoms?
Yeah, we understood that.
Okay, very good. Okay, then let's thank Mohammad once again, and the next speaker is Stephanie Jensen. So her presentation will be about what to do with an atomic model after it has been created. Is there a chance to actually compute something for it? And what is the mechanics and architecture of giving assignments to this computerized system to process those atomic models? So Stephanie, floor is yours.
Can you hear me? Is that good?
Yeah, very good.
Okay, so first build your molecule as described before, using those instructions. And today we're going to use a titanium tetrahedral. So click in the blue field to get the titanium tetrahedral, and then select the fragment and click oxygen. And then we're going to use an oxygen with 2 bonds. And then click those to fill in the oxygen, and you can see the hydrogen also shows up. So do that 4 times, and we end up with that image. And then make sure you save your file. Okay, so file, save, and name, and then save it as a .com file. So then select Calculate on this top menu bar, and then go down to Gaussian calculation setup. There's the ones we're concerned with is that job type, method, and the submit button. So first is job type, and this is what you want to compute. And we're going to use optimization for geometry optimization. You can also see frequency, spectra, and energy there. So once you click that, we now have the optimization, and then we don't need to touch anything else for now. Click on method, and then you click if it's a ground or excited state, and which theory we're going to use to solve the electronic part. So we're going to use the ground state most likely for our projects. And then we are going to use, for the method, we're going to click the molecular mechanics at first because that's the simplest option and the quickest. And it doesn't solve the electronic equation. It just uses some predefined fitting functions. So we click that option, and then we submit it. And save, make sure it's saved. So this input file contains the coordinates of your atoms, of your model, and also the set of instructions on what to calculate, to tell how to calculate. Went through that. Okay, and then once you're ready to submit, you press submit, and then you press OK. Now Gausview submits this file to Gaussian, and you can either submit from Gausview or through the command line, and I think someone else is going to cover that part. Yeah, and then the simplest way is to just do it right away, because then you don't have to exit out and resubmit it. And then, so then, depending on how large your model is, it might be right away or it might be a few minutes later. You'll end up with a screen that pops up like this, and you get this .log file, and that contains your optimized geometry. So you can see the difference. There's your old one, and then up front is your new one. So we have our product. We save this .log file, or it automatically saves. Pretty much it.
Okay, thank you very much. But thank the speaker. And other questions to the speaker about. Yes, please. Uma, please switch on the microphone.
Why do you need to do the geometric optimization after building the atomic model?
After what?
After building the atomic model, what is the necessity to do the geometric
because it'll be more accurate compared to real world. Because if you don't optimize the geometry, you could have certain angles way off. Like if you're not sure what the optimized geometry is, say you had something in the lab and you can't test what the geometry is, this would be a way to see what is the most ideal geometry that this would be in. It's used a lot in pharmacology research, where they research how different medicines, what their shapes are, and then try and work into the body of where they'll be.
Thank you.
Are there any other questions? Let me make a comment and attract your attention to what was delivered right now. So Stephanie has presented 2 important concepts. One is that Gausview and Gaussian are 2 different programs. So one program is used to build models, and another one is used to compute actual observables and do actual computation. And another important concept that we just heard, that there are 2 important files. One input file that you throw into Gaussian, and another is output file that contains results of computation. And if you do not have questions about this to the speaker, but thanks Stephanie once
Excuse
again.
me.
Yes. Do you want to ask the speaker?
Yeah.
Please.
I wanted to ask if that optimized geometry means minimum energy too.
Yes, I'm getting nods, yes.
Okay, sure, thanks.
Okay, thank you. Now. Okay, our next speaker is John Vogel, and he will cover the subject of how to run Gaussian, how to convert input file into the output file without any graphical interface, how to do it in the industrially productive way, how to do it multiple times. Okay, John, floor is yours.
Okay, so the first thing I'm going to talk about is the way that our computer system is set up. There are three main parts. We have user terminals, a central node, and then the computational nodes. The user nodes are basically any computer that has access to the central node through software such as Cygwin. And the computer nodes are what actually have all the processors and what will run the jobs that are sent to it. It's important to know that the user talks only to the central node, and the central node will talk to the computer nodes, where the users don't talk directly to the computing nodes. And so what kind of files can we submit to Gaussian? When we're submitting files to Gaussian, if you look down here on the bottom of this flow chart, where it says tio2.log, it should really say tio2.com. The files that we submit are usually in the .com format. Okay. Okay. And the way that once you are logged into the supercomputer and you have gotten into your directory, what you want to do is right here where it says this run Gaussian, the red underscore there just means to put a space. So it's the run Gaussian space and then the file name in the .com format that you want to submit to the Gaussian processing. And when Gaussian is finished with it, you can go back into the directory that you submitted it from, and within that directory, use the list function, and you should now see a new file with the same name, just in the .log format. So if you want to check if the job is complete or not, say you entered it yesterday, a command that we can enter once in the supercomputer is this qstat. When you are in the directory that you submitted from, the qstat will pull up all jobs submitted to the Gaussian programming, and it'll list the job number, the file name, and it will say C or R. It's basically telling you if it's running, if it's queued to wait, or if it has been completed. So, you know, the job submitted might actually take 2 days to run, so this is a good way to optimize your time by not constantly sitting and waiting for it. Also, let's see. Also, what is important about using the queue is that you can submit multiple files, as many as you want, at the same time, and the queue will look at how many processes are being used, and it will decide when to start a job submitted from you, or if it should wait until there's enough processing power and time to run the job appropriately. And so once we get a file back from Gaussian in the .log format, we want to see if it actually did the job that we wanted it to do. So one way to do this is to use the Gausview program that we have been looking at and opening the file that was returned from Gaussian in Gausview. And so say we were functioning and looking to optimize the geometry, we can use the tools that were described today at looking at modifying, say, the bond length, but instead of actually modifying it, just selecting the atoms and then viewing what the distances are and if they correlate to what we are expecting or what they are also, or if they're close to the experiment. We use many different kinds of file formats within Cygwin and when talking to the supercomputer. They are often useful because different programs or software want to run on different file formats, such as we have used .com and .log. You can also save Gausview as a PDB. The .png is often a useful tool when saving from Jmole, which I don't know, is anyone talking about that today? About Jmole? Yes, okay. Okay. And you can also transfer out to XRD data or just looking at coordinate data in an XYZ format. And so if we want to convert from one file format to another, the program Babel will need to be found on the internet and downloaded. It is a free software, right? Yes, it's free software. And so when in Cygwin, what we would type here is we would type Babel space and then -I standing for input and the file format in space file name space -O standing for output. Then we would put the output file format space and then followed by the file name. So in my example on the bottom, it is going from a .pdb file to a .com file. And the TiO2 is just an arbitrary file that I had pulled, that I have stored in my directory. So, and that is a way to convert files.
Okay, let's thank John. Very, very helpful presentation. And do we have questions to the speaker? Okay, it means that it was very clear. And thank you for the perfect timing. So now we do have our last in time but not least in significance presentation by Vinu, which stands for Vinatini Balasubramanian. And she will make connection between our abstract modeling to a real world. She will show how to visualize the geometry that have been optimized, and she will show how to convert the data generated in the X-ray diffraction experiments into the input files for computational chemistry simulations. So Vinu, floor is yours, please.
Can you hear me, SPSU?
Yeah, okay.
Here, good afternoon to everyone, and I'd like to present two important softwares which I learned from Dr. Killen. And Yulun, I would like to thank Yulun, current graduate student at USD, who found this Vesta software, and which is really helpful. And Jmole is a software which used to visualize the atomic models which we built, and it helps us to take the images and which can be inserted into our presentations and publications. And the Vesta is a software which helps us to build or convert. It's an easy method to convert the crystallographic information files, because there are a lot of crystal data and very big molecules which is not easy to build in the Gausview. So this software helps us to just easily convert the bigger structures into a simple format which can be used in the calculation. And here is a simple command which helps us to transfer the files between the computer and the cluster. And SCP is the command which stands for the secure copy. And here the first one shows the source of the file, where it is, and which is separated by a colon. And the second one, which is highlighted in the blue, is where the file needs to be copied or stored. And in this way, you can transfer the files between the computer and the cluster. And here is a simple introduction about Jmole. It is an open source Java viewer for the chemical structures in 3D, and this is written in Java and runs in Mac OS and Linux, Unix, and Windows system. And it supports a lot of various files, input files in the PDB format or CIF format, MOL or an CML format. And how to access this Jmole. Here are some of the useful commands. When you search the change directory to software, it will show the list of softwares, and Jmole 8 is the one which we are using it in our cluster. And when you check for the cd Jmole 8, you can type Jmole and you can enter into the Jmole, same as the Gausview. And here you can see the picture of a typical Jmole window. And how to visualize, go to the file and open the .xyz file which is stored, which is built from the atomic model. And when in the Jmole tab, you can see the third icon which shows capturing the image, and you can take the picture of the image and you can save it as a bitmap file or JPEG or PNG formats, and you can simply insert that picture into your PowerPoint presentations. And the second important software is VESTA. It stands for the Visualization for Electronic and Structural Analysis, and it is also an 3D visualization program, same as Jmole. But the one of the unique feature about it, it helps us to convert the crystallographic data into our computational files. And VESTA is also a free software which runs on Windows, Mac OS, and Linux. And here is a list of different input and output formats which can be given as input and converted into the computational files. And what we are interested is in the CIF file. In the crystal growth, as we have, you can see there are a number of steps. How to grow a crystal, choosing a crystal, and the data collection, processing, and structure solution, structure refinement, and publication. And in here, in the structure solution and structure refinement, we can see it's also can be done by Shellx software, which is a graphical user interface. And there are different formats with different softwares included in that, which is WinGX, OLX2, and Platon. And from that, we will get our crystal data as a INS, RES, or a CIF file. And CIF file is the one stands for the crystallographic information file. And this is a standard text file format for representing crystallographic information. And this is declared by the International Union of Crystallography. And so when we have our CIF file, and we can install this VESTA software, and you can open it in the VESTA, and you can export that data as you see here. And then you can save that file as a .xyz, which can be supported for computational. And also there is another format called postcard, which is a useful input file for the WASP software. And it will ask for two different types. One is fractional coordinates and Cartesian coordinates. And fractional coordinates will be saying more details about the A, B, C angle in the unit cell of a crystal. And the Cartesian coordinates will help us to save the data in the HKL files. So the one which is typically used for our calculations is a fractional coordinate. So you can say OK for the fractional coordinates. And then here is the second window is the one generated by the VESTA software, which is useful for the WASP calculations. And thank you.
Thank you very much, Lena. Other questions in the USD or SDSU? So it is, yeah, please, Uma. And please turn on the mic.
Can you save as the zip file into postcard in Jmole software? Or only you can convert using the VESTA?
What you can do is you can save it in the XYZ using the vector, and you can take that XYZ and you can view it in the Jmole.
Okay. Thank you.
Okay. Any other questions? Okay, let's thank Vin once again. So thank you all for making really nice, perfect presentations, and a special thank you for making perfect timing. So we are done 5 minutes before an hour is gone. So I believe that it will be really helpful thing for our continuation of the computational chemistry course. And if you like the presentation, the style of presenting and listening to each other, we can do it 3 times more. The last Thursday of February, we can make presentations of observables in Gaussian. Last Thursday of what is the next? March, observables in Gaussian Software, and last Thursday of April, we can make presentations on our independent research project. So what we learned today is how to build atomic models, how to create an input file that is later processed by computational software, and how to give a command to a cluster that it gets something useful from the out of the input file and converts it into the output file. And in addition, we got a proof that our activity is not just entertainment and some formal abstract things. It is connected to real experiments, to real data that can be obtained from the crystallographic data, and we can support those models with additional calculations. So thank you all for hard labor. Thank you for coming, and class is dismissed for today.
Excuse me, doctor.
Yes.
Are you going to upload these files to D2L? These
They
presentations?
are already on the D2L.
Oh, okay. Thank you.
I uploaded it 2 times. One in format 1 slide per page, and another in this notes 6 slides per page.
Oh, okay. Thank you. अब धेरै तिनीहरूले कहाँ कहाँ पुगेर के भन्न थालिरहेको छ अब बुझ्दैन कस्तो छ कि त्यो सेकेन्ड होमवर्क हेरि यो थर्ड होइन सेकेन्ड नै मैले बुझेन